Okay, so this is 7.3 trig equations. Okay, so when it comes to the equations, basically we want to solve for theta. So kind of like this, we want to, if cosine is equal to theta, 1 is equal to 1/2, right? So what degree of theta or what the radiant of theta would actually be. Okay? And then just going back to unit circle, right? That's not pretty straightforward. So if we go to unit circle, when is the x value, right? Because that's the cosine. So when is the x value equal to positive 1/2? And it's equal to positive 1/2 at pi over 3, right? And if we keep going, the next one that's happening is down here at 5 pi over 3, right? And that's pretty much it, right? You say, oh, we're done, right? It's equal to these two, and we're done. However, that's actually not completely true. For instance, what if we go a little further? So for example, what about 7 pi over 3? Does that work as well? We talked about this earlier, right? How to, find cosine of 7 pi over 3. That means you're going around the unit circle once, all the way around, and left over of pi over 3, which is right there again. Now you may say, well, that's the same exact thing. Yes, but technically it's another answer, right? These are two separate answers when it comes to it. And I could keep going and going and going. I just going around the unit circle over and over and over and over again. So the question becomes, how do we find all of the solutions this will actually use, right? Without, having to go unit circle over and over and over again. So when it comes to this, we want to find a general solution for them. Okay? And this general solution is actually quite nice. So it says, in general, our solutions are always going to be theta is equal to theta 1 plus k times p, okay? Where this k is any integer, so, numbers that are, negative and positive, but whole numbers. So they actually have to be whole numbers, in other words, right? There's a difference between them, okay? P is the period of the function, and theta 1 is one solution, okay? So let me give you an example of how this will work for our example up here, okay? So each one of these, not including that one, and this one, will be considered our theta 1. So we'll call it theta 1 and theta 2, respectively, okay? So our actual solution is going to be theta is equal to theta 1, so that's pi over 3, plus k, any arbitrage, so we're just going to call it k, times the period. So remember, the period of cosine is 2 pi, which means that is the actual general solution, as always. So I can plug in any number for k, and I'll just generate all the solutions possible. Now, believe it or not, that's actually not all of them, because we also have this one as well. So we have another theta representing the exact same concept. So now this can be 5 pi over 3 plus k times 2 pi. So this ends up being all the solutions possible just by this very simple equation. And then this is exactly what we're going to be doing here. The only difference is we're not going to find all of them. We're going to find a finite amount between them. So we're going to say, we only want all the solutions between, let's say pi and 3 pi, or pi or pi. So it narrows it down so we can actually find a nice list instead of just saying, okay, I can't really find the entire thing, but they're always going to be in this portion. Okay. So let's try another simple example. So let's suppose we have sine of 1/2. Okay. So same process we did with cosine, right? We got to figure out where is the y value equal to sine. So if you guys have your unit circuits out, you can just easily find it. So it's at pi over 6 and at 5 pi over 6. Okay, and let's suppose we want theta between 2 pi and 0. That way you can see what I mean by listing them out. Okay, now we do the same exact process we did above, right? So the general solution in our case, because of its sign, this is theta 1 and this is theta 2. I'm going to write them just like we did here. Okay, So our general solutions are going to be, so theta must equal our first one, which is pi over 6 plus 2 pi k. And the other one is going to be theta is equal to 5 pi over 6 plus 2 pi k, right? Now remember, we only want all the solutions between 0 and 2 pi. So what that means is it forces k to be positive, right? Because if I play a negative, therefore this is going to be a negative, it's not going to be in there. So I only want the numbers going to be 0 to pi. So therefore, this forces k's to always be positive at whole numbers, like 1, 2, and 3. Does that make sense? Okay. So what we want to do is just literally plug in numbers, right? So if k equals 0 in both cases, if k equals 0, this is gone. We have pi over 6. Well, pi over 6 is between what we want, so that's a good choice. And if you do k equals 0, that's gone. And then 5 pi over 6 is also between these two numbers, so those two numbers work. And then we're going to do the same thing. We're going to repeat. Now we're just going to plug in another number for k. So let's plug in 1 in for k. So if k equals 1, that means I have 2 pi. And now I just add them. So a little note over here. So 2 pi over 1 plus pi over 6 means we need common denominators. So multiply both by 6. That gives you 12 pi over 6 plus pi over 6. And that's 13 pi over 6, right? Well, here's a question for you. Is that between the what we want? So is 13 pi over 6 between 0 and 2 pi? And hopefully you say no, right? Because if you divide this, this goes into 2 times with something left over. Well, we don't want, so we want exactly 2 pi. So that's done. We can't do anything there. So that doesn't work. And now let's check over here. So if I plug in 1 in for pi, I get the same exact thing. So this is 12 pi over 6 plus 5 pi over 6. This is 17 pi over 6. And do the exact same thing. Is 17 pi over 6 between 0 and 2 pi? Well, if you're not sure, just divide them, right? So that's almost 3. So that's almost 3 pi, which is well above what we want. So that's not on there. So therefore, these are the only two solutions between what we were asked to find here. And that's what we're going to talk about, mean by a list. We're literally just going to check. That's it. So obviously, since 1 didn't work, when k equals 1 didn't work, 2 won't work, 3 won't work, so forth. So we could just stop there and these are the only two solutions between 0 and 2 pi itself. And that's what we're going to be doing this entire section itself. Just, more examples based off that information. Okay? So let's try a little bit more difficult one, a little tweak one. So what if I just tweak the last example to look like this? Okay. Now it's 2 theta on the inside. Okay, so a little tricky when it comes to it. Okay, so we can do the same thing, right? So when its sine is equal to pi, 1 over 2, and same process, right? We said it earlier. It's pi over 6 and 5 pi over 6, okay? Now, here is where the tricky comes into play, right? So if I go over here, right, this theta, this general theta was given to us. Now, this theta comes from here. So essentially what you want to do is this portion here is actually being equal to whatever is on the inside of this being evaluated. So this right here is now, so it's going to be 2 theta is equal to theta 1, which is pi over 6 plus 2 pi k. And then 2 theta is equal to 5 pi over 6 plus 2 pi k. So wherever what's being evaluated on the inside in the parentheses is actually being the general solution itself. And then from there, we actually have to solve for theta, respectively, and then do the old-fashioned way itself. So for example, if there's a 5 theta here, it'll be 5 theta and 5 theta, and then we have to divide for every single one. So now if we just solve for theta, right, divide everything by 2, this now becomes pi over 12, and the 2's cancel, and it's just being pi k. And same process over here. This becomes 5 pi over 12 plus pi k. And now we start our process, right? So if k equals 0, that goes away. And for sure, pi over 12 is within our range. So that's one of our solutions. Same thing over here. That's go away. That's also within one of our solutions. And now we do k equals 1 again. So we just keep going and going and going. So if k equals 1, we got to add these together. So we got to figure out what pi over 12 is plus pi is. Well, that's just multiplying by 12. So this is pi over 12 plus 12 pi over 12. That's 13 pi over 12. And that's definitely within 0 to pi, so that's also one of our solution sets. So we did it for 1 here. We do the same thing 1 here. So 5 pi over 12 plus 12 pi over 12. That's 17 pi over 12, which is also still within our range, right? So that's also included. 17 pi over 12. And we keep going. So when do we stop? Well, when we actually don't have any more numbers. So it worked for k equals 1. So now we try if k equals 2. So if k equals 2, we have pi over 12 plus 2 pi, and see if that's within our range. So this ends up being pi over 12 plus 24 pi over 12. So this ends up being 25 pi over 12. And if you divide this, that's 2 and something, which is not within here, right? So therefore, that's not included, which means those are all the solutions because it didn't work for 2. So that's how we kind of figure out we've got to plug in, and guess. Well, it's not really guessing, but plug in and see which ones all the solutions actually work, and then from there go from that process itself.